So chapter 8 is about the process that we use to make decisions about the acceptability of projects. So pretty much anything that we are going to be investing in, the generic word that we use for it is a project. So if I'm thinking about investing in a building, it's a project. I have to make an upfront investment with the expectation that I will have some cash flows in the future. If I'm expecting to buy a company, that's another project. I'm buying a company by either paying cash or stock upfront, and then I'm expecting to make money after the purchase of that company. If I'm trying to upgrade some equipment, or I'm trying to install some new system, that would also be considered a project. If I'm doing it in a personal level, I can also think of projects. Let's say I take off from work to write a book. So I'm going to lose some money up front, but in the end, I'm going to make some money down the road. So that would also be considered a project. If I'm comparing between service contracts, let's say I go out and I'm trying to get a service contract to maintain the air conditioning system in my facility. And I look at two contracts. One contract is for a period of 4 years, and another contract is for a period of, let's say, 6 years. And I have to make a comparison and I have to make a decision. Which service contract do I invest in? Well, that would also be considered a project. So pretty much anything I can fit within this rubric of a project. So the question then becomes, if I'm evaluating these types of projects, how do I make a decision? The decision could be to invest. The decision could be to save costs. Either way, how do I make this decision? So what we learn over here is that the general rule that we are going to be following just 1 minute. So the general rule that we will going to be following is the net present value rule, a rule that we are quite familiar with. Yes. Okay, so I'll update those PowerPoints. Yeah, absolutely. Okay, so the general rule that we will be using is the net present value rule, and the main aspect of the rule is as outlined in this formula, which is pretty straightforward. I'm going to look at the benefit from my project, and I'm going to subtract the cost of the project, and if the benefits outweigh the cost, then I do the project. If the benefits are less than the cost, then I don't do the project. So no big deal in terms of why we are using this rule. The trick over here is that we are using present value. We are not just subtracting benefits and cost. We have to subtract benefits and cost based on their present value. Why? Because costs and benefits are incurred at different time periods. So for example, the investment could be made now, but the benefits could accrue 2, 3, 4, 5 years later. So I cannot just directly take benefits minus cost. The key part over here is that I have to convert that into a present value, and then I can calculate my benefit and cost. So the logic of this rule is pretty simple. I want to undertake those projects that add the maximum value or that maximize the value of my firm. The same idea that we started talking about from the very first day when we started the course, that our main objective function is that we have to maximize the value of the firm. So whether we are making a standalone investment decision or we are making decisions based on different alternatives, I have to approach decision making in a manner such that I am maximizing value. And one of the ways in which I maximize value is through the net present value model. So here is a simple example. In exchange for $500 today, your firm will receive $550 a year from now. So from a timeline perspective, your future cash flow is $550. Your current cash flow is $500. The time period over here is 1 year, and the interest rate over that period is 8%. So what is the net present value of this benefit? I take the present value of 550. The present value of 550 is going to be 509. So I take, either way, you can take 550 and divide that by 1.08, or you can use your calculator. 550 is your future value, n equals 1, IY equals 8%, and you calculate present value, that would be 509. Subtract 500 from it, and your net present value is 9.26. Pretty simple and straightforward things that we have already done before. In essence, this 9.26 is the net addition to your value. Notice your net addition to value is not $50, not the difference between 550 and 500. That's the nominal cash difference. But because 550 is a year from now, its value today is not 550. Its value today is 509.26. And thus the addition to your value is 9.26. And since this net present value is positive, what should I do? I accept this proposition, whatever this project is. So anytime net present value is greater than 0, I will accept the project. So if net present value is greater than 0, I accept the project. In other words, if net present value is less than 0, I reject the project. And if net present value is equal to 0, I'm kind of ambivalent. Maybe I'll do it, maybe I won't do it. Maybe I'll look at other factors to make my decision. I will not be able to make my decision exclusively on net present value. Okay. So here is a recap on this one then. As you accept positive net present value and you reject negative net present value, and you're indifferent if net present value is 0. So a quick example over here. You want to buy this TV. You can take the TV home and pay nothing until 1 year, when you will owe $1,500 in purchase price. If your savings account earns 5%, what is the net present value of this offer? So again, in a very practical sense, how do we use net present value? So your cash flow today is, you can either pay cash today, or you can pay $1,500 a year from now. So we treat that $1,500 as a positive cash flow, and then we take the present value of the $1,500 that you would pay a year from now, and of course that's the net addition to your value. This is pretty straightforward. If you have to give $1 today versus $1 tomorrow, of course I will defer the payment. If I have to accept an investment, I rather accept the $1 investment today than a $1 investment tomorrow. So the basic rule is, this is the basic time value rule, that $1 today is worth more than $1 tomorrow. So since $1,500 is the same cash, whether you receive it today or tomorrow, of course, trying to defer the payment would make more sense to me. Okay, similar examples, you can work them out on your own. Here is a multi-year example. So a fertilizer factory will cost $81.6 million to build right now, and it will have cash flows of $28 million after the first year, and then last for 4 years. What should be our decision in terms of accepting or rejecting this project? We can lay it out on a timeline, or we could use our financial calculator. So pulling up our financial calculator, let's see. So on a financial calculator, this is what we would do. There are multiple ways in which we can do this. Notice over here, for this particular example, the $28 million cash flow works like an annuity. So I could use the time value keys to do it, but what I prefer to do is directly use the cash flow keys. So I go into the cash flow, second, clear work. My investment is 81.60. I change sign, enter. And then down arrow, 28 million is my first cash flow, enter. And then down arrow, and 28 million occurs 1, 2, 3, 4 times. So 4, enter. So I've entered all my cash flows. Then I go to my net present value. I go to my net present value, and now I have to enter an interest rate. So assume whatever interest rate over here, this is not given, but if I were to assume, let's say an interest rate of 10%, enter, and then down arrow, and I compute. So that would give me a net present value of 7.15. So I would accept the project if that's the case. Notice if I go back over here, and let's say I change the interest rate to 5% and enter, and I compute net present value again, what happens? Net present value goes up to 17.68. Now I go back over here, and let's say I increase interest rate to 15%, enter, and recalculate net present value. Net present value is now negative. So we can easily see the inverse relationship between interest rate and net present value. When interest rate goes down, net present value goes up. When interest rate goes up, net present value goes down. And that's also pretty easily seen if you look at the formula over here. So if you look at the formula over here, that's pretty self-evident because it's an annuity, or you can look at the formula over here. Notice that the discount rate is in the denominator. So if I increase the denominator, I overall decrease the fraction, and vice versa. So the inverse relationship between net present value and interest rates. Okay. As interest rate goes up, net present value goes down, and vice versa. So if cost of capital is 10%, then net present value is 7.2, and they should undertake the project. So this inverse relationship between net present value and discount rate is more readily seen if I look at a graph like this. So what am I doing over here? So here is our baseline that we just worked out. When discount rate was 10%, net present value was 7.2. When discount rate is 6%, net present value is 15.4. When discount rate is 16%, net present value is negative 3.3. So if I take this table and I convert this into a graph, I will get a picture like this. And this graph is often called the net present value profile, which essentially is the relationship between discount rate, and over here on the y-axis I'm measuring net present value on the y-axis. So here is our initial number. When our initial cost of capital or discount rate was 10%, our initial net present value was 7.2%. And as interest rates go down, we can see net present value go up. And as interest rates go up, net present value goes down. But here is probably one of the more interesting aspects of the graph. Notice that the NPV profile intersects the x-axis at this number, 14%. So what does that discount rate represent? That discount rate represents, you can say, the crossover point. This is where we are crossing over from positive net present value to negative net present value. Another way of saying it is that if the discount rate is 14%, then what is the value of NPV? 0. So when discount rate is 14%, net present value is 0. And given its special nature, we call that discount rate by a special name. And the special name is IRR, internal rate of return. So by definition, the internal rate of return is the discount rate for which net present value equals 0. It's the discount rate for which net present value equals 0. So we know for our net present value decision, what's the decision we make? Anytime net present value is greater than 0, we accept. So how would we make decisions based on IRR? If IRR is greater than R, then we accept. Notice over here in this example, IRR is 14%. What is our discount rate? 10%. That's what we started with, 10%. So IRR is greater than R, the discount rate. R is the discount rate. You can view R as the required rate of return, the discount rate, the cost of capital. Different names means the same thing. So if IRR is greater than R, then we accept the project. So if the cost of capital or the required rate of return is 10%, both net present value and IRR point me to the same decision. Net present value tells me to accept the decision. IRR tells me to accept the decision. So in essence, at least up to this point in time, we can view net present value and IRR as comparable methods by which we can arrive at the same decision. And both these examples use the principles of time value of money, but they arrive at the decision making slightly different. Net present value is directly giving you the dollar value that is being added to the firm as a result of accepting the project. So in this case, if discount rate is 10%, you accept this project, you are adding $7.2 million of value to the firm. So that's giving you a direct measure of dollar value. That's the good news. The bad news is about a net present value is that this value is somewhat abstract. What does it mean to add $7.2 million in value to the firm? That's not $7.2 million literally in cash in your pocket right now, because the project still has to complete out over the next 4 years. But that's the addition of value. The one way to think about value is that if you were to sell the firm before the project versus sell the firm after you accept the project, you would get $7.2 million more for the firm as a result of this project. That's one way to think about how do I monetize this net present value. But nonetheless, it is still an abstract. You don't accept projects thinking about selling firms, right? So it's somewhat abstract to think about it. On the other hand, IRR is much more direct in its measurement, because IRR is measuring what is the internal rate of return. In other words, what is the return I am getting for my investment for every dollar that I am investing in the project. So whenever I'm investing in a project, there is a cost to my dollar. No investment is cost-free. What is the cost for my investment? The cost of my investment is measured in R, because that's the cost of capital. If I have to go out and do a project, I have to raise capital to invest in the project and for me to do the project. Whether the capital comes internally or I have to go out externally and raise it, right? So every capital project has a cost, and R measures for us the cost per dollar. For every dollar that you invest, If R is 10%, that means you are spending 10 cents. The cost of spending that dollar is 10 cents. What is IRR telling you? IRR is telling you how much are you getting back for that dollar of investment. And IRR is telling you that you are getting back 14% on that dollar, or 14 cents on that dollar. So for every dollar that you are investing, you are spending 10 cents, you are getting back 14 cents. Of course, it's a no-brainer. I do the project. IRR is also somewhat intuitive for many managers, because most managers have a good sense of how much it is costing for them to invest in projects. Because they have to go out to the bank, negotiate a loan, they may have to go out into the capital markets, raise money through selling stocks or selling bonds. They have a good sense that if I have to raise capital, this is how much it would cost me to raise capital, to invest in this project. So IRR gives them a direct measure. I'm going to spend 10 cents per dollar, I'm going to make 14 cents per dollar. Of course I do the project. So IRR has that intuitive advantage over net present value, which is why it is not coincidental that more managers, by a narrow margin, but nonetheless, more managers prefer to use IRR as a decision-making tool, although conceptually, and we will not get into the details why it is so, in this course, it is a little bit outside the scope of this class, but conceptually, the net present value rule is much more theoretically sound. One simple reason is that it goes back to the fundamental principle that we started the course with. Our fundamental objective is to maximize value. And net present value gives me a direct measure of that objective. Am I attaining that objective or not? Net present value tells that to me more directly. But given the rules, given the reasons that we just talked about, IRR is a much more popular method for making decisions. Now, in addition to the net present value rule, we have other rules that are somewhat ad hoc. Not great rules, but simpler rules. One of the simple rules that is sometimes used, as you can see over here in the previous slide, with some regularity people use it, although in terms of its intellectual appeal, it's a lousy rule. It's a pretty bad rule, but still people use it. You know, people sometimes do stupid stuff. And the rule is called payback rule. The payback rule is simply asking the question, how long does it take to recover my investment? Just time-wise. If I invest $81 million, how long will I have to wait to recover that money? 2 years, 3 years, 4 years, 5 years? How long will I take to recover? And then, if I use this rule, I can apply a decision-making criteria that I accept the project if the payback period for the project is less than whatever I have decided as my requirement. And that requirement itself is quite arbitrary. So if I believe that if I make this investment, I need to recover my money in 3 years, and there may be some good reason for it, because 3 years later you may be anticipating another big investment, so you want to recover the money from this investment so that you can use it for that alternative investment that is coming up 3 years down the road. So there may be a good reason for you to have this rule, and then you can apply this rule. The fallacy of this rule is that it does not take into account the time value of money. It does not take into account the timing of those cash flows. It only looks at the amount of those cash flows. So again, going back to this example that we started with, we had $81 million that we had invested, and the project, the cash inflows was $28 million per year. So we know after 2 years, you would have recovered $56 million, $28 million in year 1, then $28 million in year 2, and then by the 3rd year, you would have gone past your $81 million investment. So you know your recovery period is somewhere between 2 and 3 years. If you want to be a little bit more exact, like get it to a decimal point exact, so you know that after 2 years you have recovered 56. How much do you have left to recover? 81 minus 56, and that would be 25. So in the third year, you are recovering $28 million, right? You're recovering a total of $28 million. You only need $25 million. So then your total time period for recovery is the 2 years plus whatever this fraction is, 25 over 28. That will give you an exact value of the payback period. Similarly, you can look at other examples on the PowerPoint to practice some of these. So here are the weaknesses of this payback rule. Of course, as I just mentioned, it ignores the time value of money. It ignores any cash flows that comes back after the payback period. For example, in this type of a cash flow situation, notice that for the first 3 years you don't recover a whole lot, but in the 4th year you make a killing. The payback period would not be able to anticipate that there's a lot of money to be recovered after the project's initial payback period is over. So it would not attach any value to this, assuming that all of the cash flow is recovered. Let's say the initial investment is not 10,000. Let's say the initial investment is only 3,000. So the payback period would be 3 years, completely ignoring that you're about to get $1 million after the 3rd year. That is not factored into your decision making. So that's what we mean over here when it says it ignores cash flows after the payback period. And of course, because of that, we would say it's not grounded in the proper economic rules that we have established so far. I already covered what internal rate of return is. So here is a recap for at 10% cost of capital, net present value is 7.2. Payback period is slightly less than 3 years, not exactly 3 years. And the internal rate of return method is 14%. So by net present value rule and IRR rule, I would accept the project. If for whatever reason I had set my payback period to be 2 years, I had set the hard rule that I need to recover the money in 2 years, or I would not do the project, then I would reject the project, essentially leaving out $7.2 million in value, which is one reason why we do not like to use the payback period as a rule. In terms of the IRR itself, as I mentioned, as we saw in this example, most of the time the IRR rule agrees with the net present value rule. So most of the time it doesn't matter which rule I use, because both rules will give me the same accept, reject decision. However, there are cases when IRR and net present value disagree with each other. So what are those cases? So one of those cases where they may disagree with each other is a situation of what we call delayed investment. Typically in a timeline and typically in projects, our assumption is investment is made today. This is my investment today. This is my cash flow today. This is my C0. That's the typical. But sometimes you may have the atypical situation where you are receiving cash flow upfront, positive cash flow upfront for cash outlays down the road. Think of if you are planning, let's say, a concert or you're planning a conference. You would sell tickets upfront or sell registrations up front, and you will receive cash. But then down the road, you will have to expend the money for whatever the event cost is. So that could be a situation like this. So if I do the net present value over here, so I enter $1,000 as my, and the way I will do this is not by using these cash flow sequences. I would use our cash flow sequences in the cash flow key. So I clear everything, go into my cash flow, second clear work. Now my CF0 is going to be 1 million. Okay, and so that's enter. C01 is going to be 500,000. I change sign, enter, and then F01 is going to be 3, right? The same cash flows for the next 3 years. So I've entered the cash flow. Now I have to calculate IRR. So to calculate IRR, I'll go here, the key that is right next to net present value. Click on IRR and then compute. So it's 23.38. So IRR is 23.38. What would be the net present value? Well, to calculate net present value, I have to know what my discount rate is. So assuming a discount rate of 10%, I go to net present value, enter 10 as my I, down arrow, and compute. 243,425. Notice what? Notice here is the conflict. IRR is 23. IRR is 23.8. 23.38. And IRR is greater than R because our assumption is that the discount rate is 10%. Okay, so discount rate is 10%. IRR is greater than R. So looking at the IRR rule, what should my decision be? Accept. Because we established the rule when IRR is greater than R, we accept the project. The rate of return is greater than the cost for the project. Okay. Now let's look at net present value. What happens? Net present value is negative. So what is net present value telling me? Reject. So now we have a conflict. Which rule do I choose? Before we answer that question, the first question you have to validate, why do we have this conflict? Why do these two rules give me two different results? And the answer is that the net present value profile, the first time we saw the graph was this downward sloping graph. This time the graph is upward sloping like this. Why the reversal? The reversal because it's a delayed investment. Meaning I am making money now and investing later. Versus the first time we saw the profile, it was a normal investment, which is I invest now and then I make money later. Anytime you have a delayed investment, so this example that we were doing over here, we calculated net present value as 243, right, as negative. So now I go back over here and let's say now I want to increase my cost of capital to, let's say, 30%. Enter, and I go back and I compute net present value. Net present value becomes positive, which is counterintuitive. Net present value is increasing as I increase my discount rate. Why is this happening? Because the net present value profile is now upward sloping. It is not the typical downward sloping because of the reversal of cash flows. We have delayed investments. That's why we get reversal of cash flows. So if I look at this from a graphical perspective, I notice that when cost of capital is 10%, net present value is positive. When cost of capital is 30%, net present value would be positive. Negative when it is 10%, positive when it is 30%. It is for this reason IRR is giving me a misleading answer. So if we have a conflict like this, we would revert to the net present value method. Since it's a direct measurement of value, that's our fallback position. So for delayed investment, we are not going to use IRR method, we are going to use the net present value method. I will not go into this in detail, but just mention this to you. Another problem that arises because of for IRR rule, without going into too much detail. Just show you over here that look at this type of an investment opportunity. I have a positive cash flow today, followed by a series of negative cash flows, then zero cash flow, and then a positive cash flow. Right? So negative, positive, negative, zero, positive. So if you follow the timeline, what do you see? You see reversals of cash flow signs. We go from positive to negative to zero, back to positive. If I were to determine the net present value profile of a cash flow sequence like this, the net present value profile would be this U-shaped curve now. Not the initial downward sloping that we had, not the later upward sloping that we had for delayed investment, downward sloping for normal investment, upward sloping for delayed investment. Now we have this U-shaped curve. What is even more problematic with this curve is that you get two IRR numbers. So which one of these two numbers would be the right number? I don't know. How will I calculate the multiple IRR on the calculator? You can't. So because of this situation, whenever you see a cash flow sequence that reverses sign in midstream over the timeline, then there is no point in using internal rate of return as a method to solve for the viability of the project. You can only use the net present value rule as project viability, for project viability. Okay. This section, modified internal rate of return, you're not responsible for, so I will not cover this. So don't worry about that. The next thing I want to go over is how do we choose when we have alternative projects competing with each other? The first part of the exercise we did normal investments and delayed investments. So in both cases, we were looking at standalone projects. I want to buy a new property. I want to buy a new factory. I want to launch a new product. Standalone decision. What are considered mutually exclusive decisions or mutually exclusive projects? If you are evaluating, let's say, two different air conditioning units for your new building, those two alternatives would be considered mutually exclusive because you can only accept one of those proposals, one of those bids. So the definition of mutually exclusive projects is that by accepting one, you automatically reject any other. If you are faced with making decisions for mutually exclusive projects, then you have to pick projects based on their net present value. Pick projects based on their highest net present value. So for example, if you're picking between these two air conditioning systems, you pick the one that has the highest net present value, it automatically rejects the other. So if there are multiple, let's say there are 5 or 6 competing bids, then you will rank the projects in the order of the net present value and select the one with the largest net present value. And this decision rule should make intuitive sense why we are using this decision rule, because again, our goal is to maximize value. So the project with the highest net present value maximizes value for us. So here is an example over here. You have been approached with an offer to buy it, buy a commercial property for $220,000. You have collected the following information about possible uses of this property. You could establish a bar, a coffee shop, an apparel store. These are the initial investments. These are the first-year cash flows. And you are assuming that these cash flows will be growing into perpetuity. But they're also growing at the rate of whatever, 3.5% or 3%. So the cash flows over here are considered a growing perpetuity. So how do I evaluate between these alternatives? Well, present value of a growing perpetuity, you know this from cash flow as well as in the stock pricing chapter, but most definitely when we went over the time value chapter, present value of a growing perpetuity is cash flow in year 1 divided by R minus G. So this part over here is present value of your growing perpetuity. So from that present value, what do? I subtract the initial investment. And that gives me net present value. So I apply the rule over here. So here is my first year cash flow. This is my R. This is my G. I subtract the initial investment. That gives me net present value. I repeat it for all 3. And these are the 4 alternatives I have. I rank them from the largest to the smallest net present value. And of course, the winning proposal would be to establish a coffee shop. So that's how I select between mutually exclusive projects. Similarly, you can practice some of these other problems. Another challenge arises when we are comparing projects that have differences in scale. Meaning, let's say one project requires an initial investment of $1 million and another project requires an investment of $100 million, but they are mutually exclusive, meaning I can either do one or the other. So how do I compare projects based on such large differences in their initial investments? So assume that if these projects were of identical scale, then of course it is easy to compare them. I can directly compare them on the basis of their net present value because they are same initial or similar scale. They don't have to be exactly the same, but as long as their scales are similar, they're not that different from one another. It's easy to use them on the basis of their net present value. But if their scales change, so for example, now what do I mean by the scale changing? Let's say this second project, I'm going to scale it up by 5 times. That means I'm going to make 5 times more investment up front, but I'm also going to make 5 times more money over here. So let me go and calculate the net present value of that. That's pretty straightforward. I get $10,000 of net present value, which is certainly more than the alternative of 4,400 for its competing alternative. So which one do I choose? On the surface, of course, 10,000 is more than 4,000. But that would be a misleading answer because I generate $4,400 of value with only $10,000 of investment. But over here, I'm generating $10,000 of value with $50,000 of investment. So if I compare only on the basis of net present value, I may be somewhat misleading. I will not say I'm always misleading, but it may be somewhat misleading. Yes, I generated more capital, more value of 10,000, but I needed more capital. So $10,000 of value approximately on $50,000 of investment, which is what, 20%, right? Get here, it is $4,000 of value, $4,400 in value on $10,000 of investment, which is 44%. So for every dollar of investment, you are adding 20 cents of value for the second project, but adding 44 cents of value for the first project. And why the problem in this comparison? The problem comes because of the differences in scale. When the scales are different, it is hard to directly compare them on net present value. So what do I do in a situation like this? Okay. There are other problems, you can practice them over here. I want to get to the solution to this dilemma. Hold on, I'm going to come back to this one in a minute. Yeah. So the solution to this dilemma is in section 8.6, which is to calculate what is called a profitability index, PI. So PI would be equal to net present value divided by total investments. So for the first case, we had $4,400 in net present value. We had $10,000 of investment, so profitability index was about 0.44. In the second case, we had $10,000 in net present value on a $50,000 investment, so profitability index was 0.220. Obviously, we select the project with the higher profitability index, which would be 0.44. So profitability index is a better method to rank mutually exclusive projects that differ in scale. So profitability index, you could do that. Okay. The last thing we want to learn in this chapter is a challenge that comes when we are evaluating projects with different lives. So this comes, for example, over here, we are looking at two alternatives, but what's the difference between the two alternatives A and B? One has a 3-year life and the other has a 2-year life. So in essence, they have unequal lives. If they have unequal lives, how do I compare between alternative A and alternative B? So notice for alternative A, first of all, notice both of these projects are what? They're cost projects. They both have negative cash flows. So I am investing $10 million upfront, and then I will have $1 million of expenses in recurring cost. This could be for like a equipment that you have invested in, like an AC equipment. You installed a new AC system, $10 million upfront to install it, and then $1 million recurring expense. Another company comes and bids for you. They tell you that we'll do the same project for $7 million upfront, but our recurring expenses down the road would be $2 million, and this contract is only for 2 years. So in a situation like this, I cannot directly compare the net present value or the present value of these two numbers. Present value for A is going to be higher than the present value of B simply because A has more years in its life. So I cannot directly compare them. So what's my alternative? So let's take a look at this using our financial calculator, how to do this, and then how to compare it to the alternative. Yeah.
So this isn't the same as depreciation. This is just...
No, this is maintenance. This is not depreciation. Okay. This is how to, so $10 million upfront, and then you have $1 million expenses. So I'm ignoring depreciation right now. Those are my cash flows for this particular project. Okay. So initial is 10, negative, enter, then down arrow, 1, negative, enter, and it occurs 3 times, 3, enter, and I go to net present value, 10% I, down arrow, compute, negative 12.49. So that's my net present value for project A. And similarly, if I repeat it for project B, I will get 10.47, but I really cannot compare 12.49 with 10.47 because they are different lives, unequal lives. So what do I do? Now, follow me very carefully on this one. This is a little bit tricky. What I do is that I assume this net present value of 12.49 as my present value. I assume that's my present value. It is literally my net present value, but I assume it's only my present value. And I ask the question that if this 12.49, I were to spread it equally over the life of the project, what will be my per year cost on this project? My total cost in present value terms is 12.49. But what will be my per year cost if I spread this cost over the life of the project? So here is what I'm doing technically now. $12.49 change sign is my present value. That's my present value now. The project A has 3 years of life. And the interest rate, the applicable required rate of return is 10%. Now my question is, what is the per year cost for this present value of 12.4 million or 12.49? I'm going to calculate, sorry, I messed up over here, let me clear again, 12.49 negative, present value, 10, IY, 3, N. I'm going to compute payment, 5.02. So a present value cost of 12.49 is equivalent to 5.02 million per year in cost. Is equivalent as if I am spending $5.2 million per year over the 3 years. I do the same thing for project B. My present value is 10.47, but this time n is equal to 2. Only 2 years life for this project. IY is the same 10%, and my payment is 6.03. So if I only compared on costs, of course in this case, if I only compared on cost, project B would look like the better project. Now this is a little bit counterintuitive. Project B has 10.47 is a lower numerical number, but it's a negative number. So negative 10.47 is better than negative 12.49. So in terms of cost alone, in terms of present value, B looks to be better. So in terms of cost alone, B looks to be better. This is the better number. But when essentially what am I doing? I'm essentially amortizing the cost over the life of the project. On a per year basis, I'm actually spending less with A. It is for this reason I cannot compare projects that have unequal lives directly on the basis of their present value. I have to compare them on the basis of these numbers, these payment numbers. And what do we call those payment numbers? Those payment numbers are described as equivalent annual annuity, EAA. So essentially I'm saying, what is the annuity value? What is the annuity number that equals to my present value number? And that's the basis on which I will make the comparison. This is generally done when we are comparing projects, cost-based project, but can also be done for any project that have unequal lives. Anytime we have unequal lives, we cannot compare them on the basis of their present values. We have to compare them on the basis of their equivalent annual annuity. It's a two-step process. Step number one, calculate the present value, which is what we did here. And then, based on these present values, calculate the per year annuity. And then choose the one that is the lowest or the highest, depending upon whether it's an investment or a cost. Okay. And that completes chapter 8. Yeah, that completes chapter 8. Okay. Any questions? Yeah. Yeah.
Oh, no.
Okay. Okay, let's take a quick stretch break, about a 5-minute stretch break, and then we'll come back and try to work on some of the problems.